Hi, welcome to the sixth section in this course. This section is about parallel streams. The section is divided into 3 videos. In the first video, we're going to talk about statefulness. So, stateful and stateless functions, how to recognize them and avoid the stateful ones. In the second video, we're going to discuss how different stream operations behave in parallel streams. And in the third video, we're going to have a look under the hood of parallel streams into the so-called fork join framework that supports them. Hi, welcome to the video on recognizing and avoiding statefulness. In this video, we will first learn how to create a parallel stream. Then, we'll discuss how parallel streams may give rise to data races, and in turn, this may require synchronization. Also, we'll see that one way to avoid both data races and the need for synchronization is to embrace the functional paradigm and only use stateless functions and immutable objects. First of all, let's see how to create a parallel streams. There's basically 2 ways. Starting from a collection, you can call the parallel stream method of the collection interface, and it will provide a parallel stream right away. From any other source, you can use the parallel intermediate operation, which turns the current stream into a parallel one. And it's important to know that these methods don't do anything at all to the data, to the content of the stream. They just set an internal parallel flag which says that any operations on the stream can be performed in parallel, so meaning concurrently by different threads. Now, what happens if you call parallel and its complementary operation sequential multiple times on the same stream pipeline? Well, it doesn't make much sense to do this because the last operation is the one that counts. So this whole pipeline is parallel. In other words, it may seem that you have fine-grained control over different stretches of the pipeline. So it may seem that some stretches of the pipeline will be executed in parallel and some other parts of the pipeline will be executed sequentially, but that's not what is going to happen. The whole thing is going to be executed in parallel because parallel is the last of these 3 calls. So here's the basic idea of parallel streams. In the parallel stream, different parts of the stream will be assigned to different threads. So each thread will receive a subsequence of data, a subsequence of the elements, and it will execute the whole pipeline on those elements. Then their results will be merged when they're finished. Much more information on how the stream is split and merged is going to be presented in the third video of this section. Now, let's consider the following example. We want to compute the total salary of a set of employees, of a collection of employees. First, let's solve it with a stateless sequential stream. And by stateless, I mean that we're only passing stateless functions to the stream operations. And as you can see, it's extremely simple to perform this operation. We start with the collection of employees, we turn it into a stream, we apply the map to int intermediate operation that will extract, in this case, the salary from each employee, and therefore turn our stream of employees into a stream of primitive integers. And then on this stream of primitive integers, we can call the special sum operation that will sum all these integers into a result. Now, suppose we want to perform the same operation in parallel by different threads. Well, we can just invoke the parallel operation or alternatively, we could have started with the parallel stream build operation, and the library on its own in a completely automatic fashion is going to assign this pipeline to different threads and merge their results into a single total salary result. Now, let's also see a couple of, let's say, wrong ways to approach this problem so that we can avoid common mistakes. So, suppose that rather than delegating all operations to the library, we want to do the sum ourselves. So in other words, we prepare a salary adder class that contains an integer and has a accept method which takes an employee and sums his or her salary to our running total. So notice that this is a definitely stateful method because it updates a field of this object. Next, we instantiate such an object, such as salary adder, and then on our stream, we just call the for each that is going to perform internal iteration, and as our consumer, we pass the accept method of the adder object. So in other words, we're going to run the accept method on every employee in the stream, and we expect at the end the adder object to contain the total salary of the employees. And as a side note, notice that the salary adder class doesn't need to explicitly implement the consumer class, the consumer interface. And that's because we're using a method reference, and as we said in a previous section, the method reference will work as a bridge from the accept method and its signature to the consumer functional interface. So, as we will see in a minute when we're going to run this code, this is working. This is going to work. It will get us the correct result, but it only works because we're running it sequentially. What happens if we turn this stream into a parallel stream? Well, bad things happen because we have no synchronization at all in our code, meaning that we have a serious race condition here because different threads now are going to use the same salary adder, so different threads are going to call the accept method concurrently, and since we have no synchronization, this is not going to work, and we're going to miss a lot of updates on the total variable. And therefore, we're going to get unpredictable and totally wrong results. And I'll show you in a minute how likely it is to run into this kind of problems with this code. So what can we do to fix this problem? Well, we have to add some form of synchronization. And the easiest way in this case is to just declare the accept method as a synchronized method. So this will make sure that if different threads call the accept method on the same salary adder, they'll have to wait for each other. They won't be able to get into the accept method at the same time. So this now is going to work in the sense that we're going to get the correct result, but it's going to be very, very slow. Last version, we may be smarter about it, and rather than declare the method synchronize, if you browse through the concurrency classes, you'll find these recently added long adder class, which is a mutable long value, which is specifically optimized for multi-threading. So it's specifically optimized to be updated concurrently by different threads. Therefore, we can switch total from a primitive long to a long adder. Therefore, we need to use it with its appropriate methods, such as add. And then we can get the final result using its long value method. And as we will see in a minute, this also provides the correct result. It's faster than synchronizing the whole method, but it's still substantially slower than the stateless functional versions. Let's actually see some data now. Here we go. We're not particularly interested in the code on the left-hand side. Let me just point out that we are running the code that I showed you on the slide on 20 million random employees. So each employee will have a random salary from $0 and $10,000. And let's focus on the output you can see on the right-hand side of your screen. So I'm running and timing all those different versions that I showed you on the slides. First version is the stateless sequential stream. So in the first version, we're computing the sum through the API of the library. So the stream sum operation, and we're doing it sequentially. Well, we get such a huge result in about 43 milliseconds. Next, we do the same thing with the parallel stream. We get a moderate speed up of a few seconds and the correct result again. Then we have the three, let's call them imperative versions. They're actually the stateful versions, where we provide a salary adder object that performs the sum. In the first version, we have no synchronization at all, so it's very fast, but unfortunately the result is completely wrong. And not only is it completely wrong, it's also different every time we run it. So I'm running it 3 times here just to show you that every time you get a completely different result, and the result is very different from the correct one. So this version is not very useful at all. Next, this version is the one where we add the synchronized keyword to the whole method. Well, we recover the correct result, but it's taking almost 1 second to do it. So this is about 20 times slower than the stateless sequential version, more than 20 times slower. And finally, there's the smart imperative version, where we use this new long adder class, and it's a lot faster than synchronizing the method. So we get down to 100 milliseconds. It's still 2 to 3 times slower than the stateless versions. Okay, so the previous examples show us that when dealing with streams, it's much better to stick to stateless functions. In other words, to think functionally. What does it mean to think functionally? Well, 2 main things: immutable objects and stateless functions. What are immutable objects? An immutable object has all final fields, and all of its reference fields point to other immutable objects. And this is in fact very common. There's a couple of standard classes that behave like this, like string and all the wrapper classes. Now, how do you update an immutable object? Well, you don't. You build a new one. That's exactly what we do all the time with strings. When you append a string to another one, you're building a new string. You're not modifying the first one. Similarly, if you have an employee called Warren with some salary, $2,500, and you want to update his salary, if it's mutable, the class will probably have a setSalary method. Whereas if you follow the immutable object approach, then you'll have to build a new employee with the same name as the previous one and a new salary. What about stateless functions? Well, we've been using this word a lot, and we've roughly introduced the term in the first section. Let's go over it again. Stateless functions do not modify the fields of the enclosing object, so the fields of this. They do not modify static fields of the enclosing class or any other class, and they do not modify the state of its arguments. Therefore, they always return the same value for the same arguments, given the same arguments. And this latter property is also known as referential transparency. Now, actually, a stricter interpretation of stateless provides the so-called pure functions. These functions should also have no side effects at all, so they should not perform any input-output, and they should throw no exceptions. In Java, we're not going to adopt such a strict interpretation of stateless. We're just going to be satisfied with having referentially transparent functions as the key to efficient and correct parallel execution of stream operations. One more example. Consider list concatenation on a custom list class called myList. So if myList is a mutable class, we'll probably have a stateful concatenation operation which works like this: a.concat_b, which clearly modifies the list A. On the other hand, if these myLists are immutable, we're going to have a stateless concatenation, which might be a static method of the myList class, which takes two lists, cannot modify them, therefore it will return a new myList C. Now, if you paid attention to the previous sections, you may have noticed a slight contradiction between our current new definition of stateless function and what we said earlier. In particular, recall that we talked about stateless accumulator functions, and we talked about these functions in the context of mutable summarizations, which are performed by the collect operation. Now, this collect operation takes as one of its arguments a by-consumer called the accumulator, and the role of this object is to update a summary object based on the next element in the stream. Now, how can such an object be stateless? Well, it cannot be stateless because it needs to modify its summary argument. So the sense in which it may be stateless is that given the same summary and the same element, it will update the summary in the same way. In other words, you should be aware that the Java documentation uses the stateless word in a rather flexible way. That was all for this video. We learned that stateless functions used in parallel streams allow for maximum parallel speedup. On the other hand, if for some reason you really need to have some stateful function, and this stateful function has shared state between different threads, then you must provide synchronization yourself because the framework does not provide any.